Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is Battery Maintenance Load Testing, Standards, Requirements, and Recommended Practices. My name is Greg Valdez, and I'm the Marketing Communications Manager for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NETA CTD and one PDH or 0.1 CEUs for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of this webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Volney Naranjo, Megger's Senior Applications Engineer. Also, to assist with the question and answer session, we will be joined by Sanket Bolar, our Substation Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Volney.
Thank you, Greg, and welcome to everybody to our seminar today. This is the agenda of the presentation we are having today. We're going to have an introduction. We're going to have a slide about the standards as a reference. And then we're going to start defining battery capacity. We are also going to define what is battery load testing. And then we explain what is the rated battery capacity for then move on to the details of the capacity testing. That's going to be the longest section of the presentation. And to the end, we're going to have the summary and then the Q&A session. So to start, the batteries, well, they are a critical component of the electrical system, but they are a device that dies naturally. The life expectancy is determined by the manufacturing process and the type of battery that you get. And usually for the vented lead acid batteries is around 20 years. For the valve regulated batteries, it's around 10, 15 years or even lower than the 10 years. And all of these expectancy is seriously affected by the operating conditions. Just having a charger not set correctly, it's going to be affecting the life of the battery. Temperature conditions, operating conditions is going to be also a big factor in how long the battery is going to last. And also the maintenance practices, having good or bad maintenance practices is going to seriously affect your battery. And so we require periodic, or batteries require periodic maintenance and testing to be able to achieve that expected life. Standards and industry practices have several maintenance testing methods to determine the condition of the battery and to determine if the specifications of the battery are being met, or if the quality of the batteries is really what we purchased, or to determine if the maintenance practices are being effective. Several of these methods are listed here. The float current, which is probably not the best way to do it, but it's one of the methods that it's followed. Then you also have the ohmic testing, which is a very good method and allows you to do the test anytime without any effect on the battery and provides you very good trending data. And then you have the capacity testing, which is the one that we are talking today. This capacity testing, also called load testing, is the only proven method to determine the actual value of the capacity of the battery. It's also the only way to determine what's the state of health of the battery, or the only way to see what is the remaining life in the battery. The other methods are just an indication of what could be that capacity, and there's no direct correlation from those methods to the capacity, to the actual capacity value of the battery. So it's the best test that you can run on a battery. However, it is a very demanding test. You require sometimes very big load banks, or you need a lot of time, or you need a lot of preparation, and things can go wrong during the test. And running the test again, it's not as easy as any other electrical test. So you need to start from scratch, from zero, with the preparation, and well, some things you may not need to do, but it involves a lot of time. So understanding the test procedure, preparing the battery, and logistics are crucial for a successful test. And that's what we're going to talk about today. The world of the batteries, we have a lot of standards. Each type of battery has its own standard, and with recommended practices for the maintenance, for the installation. So that's what we can use for reference, and it's strongly recommended to follow those standards, because professionals have met and put together these documents to guarantee that you can do a very good maintenance. So everything is well explained in the standard, and you have a lot of guidance there. So each battery has its own document. We have the lead acid batteries, that is IEEE 450. Also, for the valve-regulated lead acid batteries, we have 1188, and for nickel-cadmium batteries, vented nickel-cadmium, we have 1106. Those are the three type of batteries that we're going to be referring today to. Everything that I'm prepared for this presentation is related to these type of batteries without doing direct reference to them. It's mainly everything that we have here in these slides will relate to these batteries, and there are some notes there to distinguish between them. Also, in the references here, we have NERC PRC 005, because it is basically a document that most of the utilities need to follow, and it's a requirement. And this document, or this requirement, this regulation, they ask for, in addition to other maintenance practices, there's two tests that they allow to verify if the battery is performing to the requirements of the substation. So this is the ohmic testing, or the performance test, or the modified performance test. So these two last tests, performance and modified performance, are capacity tests that we are going to be talking today. We're going to be talking about today. So let's get into the battery load testing. The first thing to mention about or to define is the battery capacity. This is the amount of energy that a battery can store at any given moment during its life cycle. So the battery is manufactured to meet certain capacity, and that is defined by the manufacturer. And once the battery starts its life, it will deteriorate, it will degrade, and that capacity will degrade, and it's going to be losing its ability to store energy. And that's what we want to verify. This battery capacity is defined during the design process. So whenever the substation or whatever facility the battery is going to be supporting is being designed, the designer collects a group of data, some data, to be able to define what is going to be the capacity that is going to be purchased. And very important in this process is the duty cycle of the load. So the designer needs to know how the load is going to behave and how long is expected for the battery to support that load in case of a power failure. Also, very important, the minimum voltage that the load can work with. And this will also define the size of the battery and other factors as the operating temperature, the design margins, and of course, aging factors. All of these defines what is the size of the battery, what is the capacity of the battery that it's going to be installed for a facility. And as this battery ages, the capacity decreases, and this is where testing is required. We need to check if the battery is holding its capacity or if it's deteriorating or if the maintenance practices that we are performing are being effective or not. So the testing, again, the main test that you can perform on a battery to determine that capacity is running a load test. And there's three reasons that you will perform the test. You will do the test to determine if the battery meets the specification or the rating or both. Basically, you are measuring the capacity of the battery, and this is usually when the battery is new, when you are accepting the battery, when you are installing the battery for the first time. From that point on, you can do the test periodically to determine if the battery is performing within the limits, if it is capable to support the load, or to be able to determine if the capacity is deteriorating or not. And then another test you can perform, or another reason you can perform, is you might not be interested in the total capacity of the battery. You just want to know if the battery is capable to supply the load for the time that you need the load to be supplied. So that is another reason you perform the test. So these three type of tests, they define or these reasons to test, they define four type of tests, which are called the acceptance test, the performance test, the service test, and the modified performance test. And these will provide the capacity except the service test. The service test is only a test that can verify the ability to meet the duty cycle of a battery. In this presentation, we're going to be talking mainly about the acceptance and the performance test, which we are defining now. So the acceptance test, it's an approval test of the battery capacity. It can be performed at the manufacturer facility or on-site after the installation, right after the installation. Usually is performed in the very first 6 months of once the battery has been delivered and installed, and it's been under floating conditions for a while. So the battery capacity has developed fully, and that is when the test is performed to accept and to also get a benchmark value. You want to know what is the capacity that the battery is starting with. The battery should be prepared and inspected with other recommendations that are in the standard. And as the result of the test, the battery could be at least, or should be at least 90% of the rated capacity. And this could be because, again, the capacity of the battery is still developing and has not totally formed. So this value is accepted, but at least should be 90%, should not be below that. And of course, it can be higher than 100%. And as a matter of fact, it usually will be like that. It will be higher than 100%. And whatever result is obtained can be used as the baseline for the trending. Then we have the performance test. This is a test that you do basically as a maintenance test to determine if the battery is holding its capacity and it's aging as it should be, and it's not having accelerated aging. The test should be made within the first 2 years of service, and then it should be performed periodically from this point on. The test interval should not be greater than 25% of the expected service life. So we have another slide that shows an example or depicts this better. But if the battery is expected to last for 20 years, well, the expectation is to test every 25%. That means every 5 years. The duration of the test, we want to discharge the battery, or we want to apply the load to the battery for a duration that is similar to the duty cycle of the battery. So we are not going to mimic or to do exactly the duty cycle of the battery. We're not gonna repeat that, but we want to have a duration that is similar to what the battery is supposed to supply. These will totally guarantee that the result that we are getting is the right result. Once the battery shows degradation, for example, the battery capacity drops more than 10% from the previous test, we need to start testing annually. Or whenever the battery has reached 85% of the expected service life, then we should also start doing the test annually, because from this point on, the battery is expected to drop faster in capacity than it does in the previous years, on the early years of the battery. So if there's like a knee point in the behavior of the capacity of a battery, it starts degrading, and then it reaches a point where it starts dropping very fast. And that is expected to be around the 85% of the life of the battery. This value is the one that we trend, and also it's an indicator of the maintenance. If we see that the battery is degrading faster, probably the maintenance practices are not good, or the operating conditions are not good, and this can evidence the situation easily, or it could also be an indication of the battery manufacturing process that might not be the best. So always try to look for a very good battery when you install something in your substation or your facility. The battery needs to be prepared for a performance test, and depending on what you are doing, if you're trending for capacity or you want to reflect the maintenance practices, you want to prepare or to not fully prepare the battery for the test. So that's some slides ahead, and we're gonna touch more on the preparation of the battery. The other two tests, the service test, it is a test that is scheduled at the discretion of the user, of the owner. It's like an audit, a surprise audit on the battery. And that's the reason there's no schedule defined for these. And it's a test that has to be performed in the as-found condition. So no previous maintenance, no previous preparation procedure. And the test has to be performed with the duty cycle, or the idea is to profile the load to mimic the actual duty cycle of the battery, or as close as possible. In this slide, we're seeing like a typical profile that comes, this is an image from the actual IEEE 485 that specifies how to calculate or size the battery, and this is an example they have there for a load profile. And the table that it's next to it, it shows the different loads that we would have to consider, and the battery is supposed to be able to meet those requirements. Whenever you have continuous load, a permanent continuous load, it should be able to supply it. And whenever non-continuous or momentary loads are required from the battery should supply them, and that's what you're trying to achieve with that test. And then the modified performance test is it's a test that can do both. It will do the profile, and then it will continue once the profile section or the duty cycle section of the test has finished. Then the test is continued with a constant current from the manufacturer's tables, and then you get the capacity. So you are verifying both aspects, the duty cycle, and you're getting the capacity value of the battery. This test is a little bit more complicated than the other ones, and you need to include aging factors in the calculation of the rate, the discharge rate. And well, I suggest that you refer to IEEE 450 for specific details for these. There are 3 types of modified performance tests. So we are not covering this one here. We'll need more time for this. Any load testing, periodic load testing, will provide an immediate demonstration of the battery capacity or the ability. You get the result, and you can use that to trend or to define some corrective actions. These recommended practices are best suited for different type of batteries, battery applications, and installation conditions. And sometimes it's not possible to follow all of these guides and all of these recommendations. The test is, as I said, is demanding, and sometimes you cannot comply with everything that is in the standard. So if you consider, or if you need, you may use alternate methods, or you can introduce variations to the recommendations. However, there's 2 things to consider. First, if you need to follow or you need to comply with NERC only allows performance, modified performance, or ohmic tests for lead-acid batteries. And for nickel-cadmium batteries, it only allows the performance or the modified performance test. So in that case, you really don't have too much space to introduce alternate methods or do some variations of these recommendations, because, well, NERC indicates that you should follow IEEE for the tests. And then, again, if you have some variations or you use any alternative methods, the rate duration, if you select a rate duration that it's not including the actual duty cycle, so basically it has to be similar or higher than the duty cycle duration, then the performance of the battery may not be fully demonstrated. The other way to say this is that short duration tests will not predict the long duration performance, and vice versa. Long duration tests will not predict short duration performance. And the reason for this is that at high rates of discharge, when you use very high currents to discharge and you want to try to make a short test, then the ohmic value of the cells and the interconnections will affect greatly the performance of the battery. So there's an efficiency factor in the cells that should be considered when selecting the rate of discharge. Okay, so we already defined battery capacity, and now we need to see this from the perspective of the manufacturer, the rated battery capacity. We already talked about the capacity that is needed in the substation and what we need to do to verify this capacity. But then when we purchase a battery or when we get to a battery, we need to know what its rated capacity. This is a value that is assigned by the manufacturer through the manufacturing process, and this is a value that is given for a specific temperature and to a specific end of discharge voltage. So any manufacturer will have what it's called the discharge tables. And here you're going to see, as you can see here in this slide, that there's voltage per cell. And let me turn on my pointer here. So you have a voltage per cell. That's the lowest voltage that the battery should be discharged to. It's also called end voltage, terminal voltage. And this voltage is also, or this table is also referred to a temperature, 25 degrees C. This means that if the battery is not operating at this temperature, it's not going to guarantee these values that are given in the table. The rated capacity of a battery is given in amp hours. And for example, a battery that has 800 amp hour as a rating, that means that this battery can deliver 100 amps continuously for 8 hours. And well, you would think that this can be that this will be a linear ratio. Well, it is not a linear ratio. It doesn't mean that the battery can do 200 amps for 4 hours, which will be also 800. This doesn't happen with the batteries. You can see here with this example, for 8 hours, it can deliver 100 amps. So that will be 800 amps hour. However, for 4 hours, it can only deliver continuously 176 amps, which is less than a total of 800. So the tables have to be followed to be able to get the actual capacity. To get an accurate value, we need to follow the tables, and we need to be sure that the battery is operating at that temperature, and if not, we need to use a correction factor, and we're going to see that later on in the presentation. This rated battery capacity is also another way to define it, is that it is the ability to deliver current at a specified rate. So the capacity testing that we have been mentioning a lot, it's actually discharging the battery at a constant current using that current from the manufacturer's table, or at a constant power. The tables are also provided in terms of watts instead of amps. But the idea is that if you're running the test to determine the capacity value of the battery, it has to be performed at a constant current or constant power. And you need to measure the time that the voltage takes to reach the end of discharge voltage that we mentioned previously. So these 1.75 volts per cell times the amount of cells. So if you have a battery that is 60 cells and the voltage, the end voltage is 1.75, means that you need to run the test down to 105 volts. And if you have a 24 cell battery, VLA battery, then you have 24 cells times 1.75. That means you need to run the battery down to 42 volts, like in this example. And once the battery reaches that point, well, we have the time, and we also stop the test. The test has to be stopped there. The voltage cannot go beyond that. If not, the cells will be affected in its chemistry and its capacity, and probably won't be able to recover that. So the capacity calculation actually compares the time that it took for the battery to reach that voltage, and it compares that to the expected time from the battery manufacturer's published ratings. This ratio is the capacity. So here you see the formula from the IEEE standard. You have TA, which is the actual time of the test. You have TS, which is the expected time. And I mentioned a correction factor for temperature. So here's the correction factor for that temperature. And we're going to see the table also later. That table that contains the correction factors. And here we can see, for example, the battery in a new condition should last for 10 hours. And then during this test, it lasted for 8. That means that the battery has an 80% of capacity. That's the basic concept about the capacity calculation. It's a ratio between the actual time and the expected time with a temperature correction. Now, this is one of the methods to calculate the capacity, and it's called the time-adjusted method. The formula that I just showed is that one, the time-adjusted method. There's another method which is called the rate-adjusted method, which we are not going to cover today. The time-adjusted method is kind of the typical test that, or the typical method that is used for tests higher than 1 hour, longer than 1 hour of duration, or 1 hour and longer. The rate-adjusted method should be used for tests that are less than 1 hour. However, the rate-adjusted method can be used for any type of test and for any duration. And actually, it's a bit more accurate than the time-adjusted method. However, that method is more complicated. You need to consider correction factors, so that's why it is not that common. So no matter what method is used, the recommended practice is to replace the battery if the capacity reaches 80% or is below 80%, the manufacturer's rating. And whenever this replacement is required, the standard allows for or gives 1 year for the replacement. So basically, you find out that your battery reached that value and you start working on the purchasing process, and well, you have 1 year. The reason for this, again, remember I already mentioned the capacity of the battery will have a knee point where it starts dropping faster as it ages. So there's not too much time to make any correction or to replace the battery. So you should start working on this soon. So here's the example or the slide that depicts the testing schedule. The idea is that you perform an acceptance test at the facility or at the manufacturer's facility or at the site once it is installed, and around the time of installation, usually somewhere between installation point and 6 months. And then within the first 2 years of the life of the battery, you run the performance test. You run another capacity test. And from that point on, you perform the test every 25% of the life of the battery. That means if you have a 20-year battery, a battery that is expected to last for 20 years, you would perform the test at 2 years of age, and then at the 5th year, then, at the 7th year, 5 years more, so 7 years, and then at 12 years, and then at 17 years of the battery. And from that point on, you start testing annually because it is around the 85% of the life of the battery. So you will do probably 5 or 6 tests on a battery throughout its life. So that's a thing that you will hear, that the capacity test is destructive. Well, it's because it's taking life out of the battery. Really, you are just taking 7 cycles throughout the entire life. And batteries are designed for a much bigger amount of cycles. So really, you're not taking too much out of the battery. Another reason that could be considered destructive is because, well, if you don't handle the test properly and you don't stop the test when the battery reaches the end voltage, it will affect the battery. But it's not the test itself is destructive. If you're not careful running the test, you could of course damage the battery. But the test itself is it's not destructive. It's the same with insulation test. If you apply a very high voltage to an insulation that is not rated for that voltage, of course you're going to break down the voltage, the insulation. So it's matter of good practices and good handling of the test and the elements that you use for the test. So the procedure for the test, how you prepare the battery and what procedure you need to follow. So the battery definitely needs preparation. I always say that it's like running a marathon. This battery is going to show you how much it can do, and you want it to be prepared and to be in good condition. So you need to perform maintenance, and you also need to do some preparation steps that we're gonna see in the next slides. The other thing that you need to consider as part of your procedure is that the battery is going to be unavailable during and after the test for a certain amount of time. And this unavailability might affect the resources or the time that you can run the test or that you have available for the test, and might also require some backup for your battery or for your facility, for your substation. To perform the test, you need the discharge table, so you need to know what are the recommended manufacturer discharge rates. You need to define what's going to be your time for running the test. You need to measure the temperature before starting the test. You need to consider your load bank, the test instrument that you're going to be using. You need to calculate that, how big it's going to be. And you need to perform some voltage measurements before the test and during the test. So here's the IEEE recommended procedure. First of all, you need to equalize. Now, here you need to check with your manufacturer, battery manufacturer, if the battery should be equalized, and this applies especially for the VRLA batteries. So VRLA batteries, they should not be equalized with the similar conditions or under the same procedures as the vented lead acid batteries. So check the manual or contact your battery manufacturer to see what is the recommendation about equalized process. And if the battery is equalized, it needs to float for a minimum of 72 hours prior to running the test. This means that if you need to start the test or you need to rerun the test again for any reason, then you have to wait for the battery to reach the fully charged condition. And once it reaches that condition, then you have to wait for 72 hours for it to float, and then you can run the test. This is one step that if you want to reflect your maintenance practices, if you want to see if the battery is really having the capacity that you are expecting due to the maintenance procedures, you want not to equalize. You want to skip this process. The second step is to check the battery connections. So you want to check all the terminal resistances, the strap resistances, and you want to perform maintenance on this if you see something that it's not good. Now, if you just want to see how your maintenance procedures are affecting or improving your battery, probably you don't want to do this prior to the test because you want to see how things are in real life, not with a battery fully prepared. Then you need to record all the floating conditions, float current, float voltage of each cell. You also need to record all the electrolyte conditions and, well, this applies for VLA batteries, for vented lead acid batteries, or for vented batteries, because this could apply also to NiCad batteries. And this is the moment that you determine what is the temperature of your battery. And this is, remember, this is a value that is important for the capacity correction factor. So, and if this is a VRLA battery, you should take that temperature from the negative post of the battery. Then measure the battery float voltage. So now, before it was in step number 3, it was the float voltage of each cell. You also want to measure the float voltage of the entire string of the battery at the terminals of the battery. And then you start getting ready to disconnect the charger, and to, if you are connecting a backup, then this is the moment that you do that, and you take all the precautions to avoid any disconnection of critical loads, and you try to perform, to follow all your internal procedure to avoid any problem with the system. And at this point, the battery, you can disconnect the charger and do the connection of the instrument to perform the test, and the battery is ready for testing. So as you can see, there's like a very detailed process to get the battery ready for testing. And if anything goes wrong, well, you need to probably go through all of those steps, or most of those steps again, and again, that's going to represent time. The connection of a load bank, well, it depends on what load bank you have. Here, this slide is showing our Torquil 900, which is a load bank, the load bank that we offer for this type of test. And it is also showing the connection of individual cell voltage monitoring. This will monitor the voltage of each cell throughout the test, and on top of the overall voltage that the Torquil is monitoring. So it's a simple connection, and you get a lot of information from this kind of setup. This shows the discharge results. It's a quick slide. It's a slide with kind of a basic information I wanted to put there, just to show how the results will show once you finish the test. And of course, this is not the entire report. I'm just putting the highlights here. Basically, you get the voltages, the numeric values. You get the float voltage, open total voltage, start voltage, and the end voltage, which is very important. Remember, you want not to damage the battery by going below the end voltage recommended by the manufacturer. And of course, you get your measured capacity, you get the corrected capacity, and the corrected percentage capacity. You can see also there the total duration of the discharge and any pause time. If the test was interrupted or there was any pause during the test, it will show there, and you will see that also in the graph. We have some examples, or one example later on. So I showed the connection and I showed the result, but there's a lot of things in between that. You need to define your discharge rate. You need to select your discharge rate. So we already mentioned that, well, you need to use the tables, but the fact that you have several options there, you have 1 hour, in this case, 1.5, 2, 3, 4, 5, 8 hours options, and you even have minute options. It doesn't mean that you can use these interchangeably between tests, or that you can select one of these rates arbitrarily. You, as again, very important, you need to look or to mimic or to look for a duration that includes or envelopes the duration of the duty cycle. And these will define your preparation, your logistics, and resources. So if you select a very high rate, well, this means that you need a very big bank, and remember that that is also going to affect your result. Higher rates will mean less efficiency of the battery. Also, if you are getting prepared for the test, you need to consider the availability. You might have, if you don't have all the means, you might have the load totally offline, or you might have that depending just on the charger while the battery is being tested. But if something happens, then you lose the charger and you don't have a backup, or you have to consider a backup. So these are things that add a cost to the test, and also all of the preparation and the resources that you need to consider. Short duration rates, you need a big bank, a bigger load bank. You need good cables and terminals for the connections, and you need to consider ventilation or installing the load bank outside the battery room. If you have long duration test, low rate test, this will conflict with the availability of the system, or you need to bring a backup. And of course, you need higher man hours to perform the test. So there's a trade-off here when you select the rate, but especially it's not really that you can select from any value. You need to select according to the duty cycle of the battery. So the performance of the battery, when you select that rate selection, when you do the rate selection, you are going to be affected by the battery efficiency. And the other thing is that once a duration and a rate is selected, it should be used for the life of the battery. So the test every 5 years or whatever periodicity you select, you should run the test with the same rate. So that is something to consider as well, that you always going to need to have the same resources to be able to run that test, and that is going to affect your costs. So if you're considering a temporary backup, this is a couple of the things that I've seen. I have 3 examples of what I've seen as temporary backup. So this is the simplest one that I've seen. It's made out of car batteries, and this is something that they bring in a truck and they put it together. They have the jumpers to set up everything here, and then the cables from the battery are run to a disconnect switch. So this is not so improvised. This is something that they have already considered in their design. The transfer switch is here, and from this box they can connect the new battery or put it in parallel with the existing battery, and then remove the battery to be tested from the system, and the substation doesn't see any problem there or any variation. So this is a very simple and quick and very low cost solution. Then you can have something more elaborated, but still a little bit of homemade, still with batteries from car batteries and in a charger mounted on a little pickup truck. And you can see there also that there's the load bank that they use to test the battery at the facility. And there's a little bit of a switch box here, or some protection here. It's a homemade solution, very simple, but very, very effective. And then you have a more industrial or professional solution, a trailer with everything with very good specs and good design, considering many aspects from multiple batteries, good batteries not or batteries according to the application that they have. In this case, they have two chargers here, and they have gas monitoring, they have ventilation, and the trailer also includes the load bank. So it's a more professional solution, and you can see from here that you can manage some of the costs of these solutions. Also, when you're running the test, you need to consider the temperature. Remember that the batteries are specified for a certain temperature, usually 25 degrees C. I've seen also batteries specified to 20 degrees C. Whatever it is, you should always get your temperature before running the test. At the beginning of the test, you should know what is the temperature of the battery, not of the room. And then that should be used for the correction of the result. When you are reviewing the results, you should always look for that temperature of the battery, and you should confirm that the result was corrected for that temperature. The IEEE includes those tables for you to correct. Here we have the example of the table for the vented lead acid batteries, and this is for the time corrected method. Also, during the test or even before starting the test, you need to determine the voltages of the battery, of the terminals of the battery. And we recommend doing this throughout the different stages that you see when running the test. So you get there, the charger is still connected, so the battery is floating. You want to measure the voltage, the floating voltage. Then you disconnect the charger, and there's a time there that lapses between you disconnect the charger and you start the test for the connections and getting everything set up. So that's that time the battery is being without any float voltage there. It's not being charged anymore, and that is what it's called the open circuit voltage. This voltage might depending on the condition of each cell, the cells might drop a little bit or might drop a lot in the voltage. And this is an indication that the battery might fail during the test. So you want to take some provisions for this to be avoided, or you can decide not to run the test because of this voltage situation. So here we see a result, a typical result again, the discharge curve, and the different voltages at the voltages at different stages. Here, another example, and this includes a pause. So the standard allows for a pause in the test, especially to do a bypass of a cell, to remove a cell from the string, because this cell might be failing. So when you pause the test, the battery is going to rest, let's say, and it's going to recover a little bit of the voltage, and basically it's recovering a little bit of the capacity. So if you pause the test for a long time, you're going to affect your result, and it's not going to be an accurate result. So that's why the pause is monitored. And in this result, we can see that the test was paused for almost 2 minutes. And you can see the effect of that here. So just with 2 minutes, the voltage went higher, and it takes a while to return to the previous voltage. So it's extending the time that the battery can run, which means that it is extending or increasing the capacity of the battery. So I just mentioned bypassing a cell. So not all of the cells discharge equally. Depending on the condition of the cell, or depending on the charge condition of the battery, the cell might run longer or faster or out of capacity. So you want to monitor each of the voltages or the individual cell voltages. The recommendation is to measure the float voltage of each cell, and during the test, at least to have 3 more sets of measurements at the beginning, at the completion, and during the test, anytime during the test. However, the idea is that it's preferable to do a continuous measurement of each cell, and that's why manufacturers have these individual monitoring devices. And by doing this, you could identify if a cell has a reduced capacity, and you can make some decisions from those measurements. So here we see the discharge curve for 24 cells. You can see that there's no variation. All of the cells discharge almost equally, and they have a very, very similar pattern of discharge. That means that it's a very healthy battery. In this case, we see a little bit of difference, and we start seeing some cells that are deviating, not showing the same pattern. They are discharging faster, and you can see that some of them will discharge, will have the same pattern at the beginning. Others will be totally different from the beginning. And the ones that are the same, you can see that they start deviating or differentiating throughout the test. So this helps you to determine, again, if there's any problem with individual cells. And here we have another example, and this is a more critical example. You can see that there's 3 or 4 cells that are having serious issues here, that they are dropping the voltage very fast, while the other ones are still with very good voltage there, with very good capacity. So definitely it's something that helps a lot to determine the condition of the cells. And it's actually critical to decide if you need to bypass a cell during the test. And this is something that is allowed, and it's in some cases is required or needed. The reason to bypass a cell is to avoid further damage of the cell, or to avoid negative contribution to the test, which is basically a polarity reversal. The voltage can go so low that it will reverse its polarity and will start being a load instead of being a source inside the string for the test. Then this bypass should be considered if the cell voltage approaches the polarity reversal, which is around +1 volt, or if it goes below that. And when the cell is bypassed, the overall battery end voltage should be recalculated. You are removing a little bit of voltage from that end voltage, so you need to recalculate it. For the VLA and the VRLA batteries, it is not required if the test is beyond 90% of the expected time. But if this happens early in the test, the cell should be removed and bypassed with a jumper. And this means that if you can, because you have very short time, you should not exceed more than 10% of the duration of the test, or 6 minutes, whichever is shorter. So you should be prepared for this. You should, if you suspect that a cell will be failing during the test, you should have a jumper and run this procedure with all the safety precautions to avoid any harm or any damage to the operator or to the technicians, and also to avoid interrupting the test farther than it is, because then if not, you're going to have to start again from the beginning, and including all the preparation time. The NiCad batteries, they are not damaged by the polarity reversal, so no need to bypass the cell during a test. However, if the cell goes beyond that minimum voltage or that end voltage established by the manufacturer, and if it goes into polarity reversal, then the end voltage still needs to be recalculated. So you don't need to stop the test, but you need to recalculate the end voltage of the test. So this is pretty much all the material we wanted to show today. As a summary, the battery load testing is the only proven method to accurately measure the capacity and determine the state of health of the battery. You need a lot of balance between the resource and time for the test, and again, it can turn into a cumbersome and a complicated test if you are not well prepared. You have very good references for the test. IEEE has a document for each battery, so it's strongly recommend to review these documents and to know them well. There's also a great amount of information that is logged during the test, specifically if individual cell voltages are recorded. Pay attention to these voltages. Don't just go and analyze the percentage capacity of the battery. There's more to analyze beyond that value. When reviewing the results, carefully check for the average temperature and confirm the use of a correction factor. And always compare to previous results to determine degradation of the battery, and verify that the tests were performed with the same rate, so you can actually compare results. If not, the comparability it's going to be difficult to achieve. Review all of your voltages in the test report, and understand and use the manufacturer's tables correctly. So with this, we conclude the actual technical presentation. Last portion of the presentation is to show the recommended equipment that we have for this test. So as a load bank, we have Torkel 900, an instrument that you can use to run any of the tests that we mentioned today. You can do performance tests, modified performance tests. It will give you the capacity value. It will actually even log the battery charging process. Once you completed the test, it can be left there connected to monitor how the battery charges. The maximum dissipation maximum dissipation power of the unit is 15 kilowatts. And if you need more dissipation, you can expand the system by adding extra loads, which are called the TXLs. Then for the individual voltage monitoring, we have the VVMs, which are a string of little boxes that you connect on each cell, and they will automate the battery voltage measurement. And they are connected, daisy chained. You can measure up to 240 cells, and you can measure strings of up to 600 volts. So it's a very flexible system that you can use for many applications, and you actually can use the VVMs independently without the load bank, the Torkel. And all of these, we have PowerDB software that will collect all your information, will create database. You can do trending, and you can do asset organization. You have all of the reporting capabilities there, and you can, if you have a compliance to meet, then you can have a compliance scheduler in the software as well. Well, thank you so much. And Greg, now I turn to you so you can give the last information from these slides, and also then we will go to the Q&A session.
All right, at this time, the presentation portion of the webinar is officially concluded. We'll now take 30 minutes to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those that are leaving, when you close the webinar window, a survey will pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there is a field where you can also request a demo or quote on any of our Megger products. Again, a copy of this presentation, along with a link to the video recording of this webinar, will be emailed to everyone in about a week. You can also view recordings of previous webinars on our website at us.megger.com. www.megger.com/webinars and register for next month's webinar, Dielectric Frequency Response and Analysis of IEEE Guide C57.161. The presenter will be Dr. Diego Robalino, Megger Principal Engineer. Now, let's get to your questions. What are your thoughts on lithium-ion batteries to replace lead-acid battery? And are they safer than lead-acid types?
Okay, so lithium-ion batteries, definitely they are new technology that they are starting to show different installations, different facilities. The cost of these batteries is still a little bit prohibitive for the substation world or substation application. However, we are starting to get calls on customers asking how to test these batteries. Related to capacity testing, the test will be the same as we just described in the general concept. We want to discharge the battery down to a minimum voltage and check if it is giving us the capacity that it is in the nameplate or how that capacity is degrading. So in regards of how is that going to be working for the substations and if they are going to replace them, well, there's still a long run for that. The lead acid batteries are still good in regards to capacity. They're still good in regards to many other technical aspects, but especially on the price side. So probably for other applications, but not for substations yet.
All right, so for our next question, one of our utility clients rejects to perform a battery capacity discharge test, flooded lead acid batteries, with the argument that the test is damaging the batteries. Do you have any experience or comment about that?
So this we touched about on the presentation. However, I wanted to answer these again because it's a very common question. It's a very common concern. The test is considered destructive for a couple of reasons. One is that every time you discharge the battery, and depending how deep you go in the discharge, you are taking a cycle out of the battery. So the same way that the batteries are spec for time, for a certain life expectancy in regards to the years, there's also a certain spec, or there's a spec there for the cycles on the battery. So every time you take a cycle out of the battery or you cycle the battery, you are taking a little bit of the life of the battery. However, depending on the amount of cycles that the battery has available, you will not be damaging the battery. The other reason that the test is considered destructive is if you go below the minimum voltage or the end voltage specified by the manufacturer, then the chemistry is going to be affected, and in that case, you are definitely going to affect the ability of the battery to hold energy. So you're affecting the capacity. But as I mentioned during the presentation, if you handle the test properly and you do the things in the correct way, you're not going to be affecting the battery. So that is very important. Do not go beyond the minimum voltage or the end voltage, and following the testing schedule that we mentioned, every 25% at least, then you're not testing the battery that often that you're going to be taking too many cycles. So in the end, it's as any other test in the electrical world, that if you don't use it correctly, you can destroy the equipment. But if you use it correctly, it's going to be a safe test, and it's not going to be affecting your battery.
All right, the next question. Can you explain the statement about test interval should not be greater than 25%?
Hi, Sanket here. So the test interval refers to the time between tests And what we are referring to when we say 25%, we say 25% of service life. Service life is the life for which the battery is expected to be in operation, and that's provided by the manufacturer. Typically, it varies from model to model, but it's typically in the range of 10 to 20 years. So you can look at the manufacturer's specs and find out about the service life. Based on that, you can decide how often you want to run the test until you see the capacity degrading.
All right, next question. Why has ANSI/NETA chosen to remove guidance on cell internal ohmic values for vended nickel-cadmium batteries in MTS 2019 Part 7.18.1.2? The 2015 standard contains specific guidance.
So I don't know exactly or don't know the exact reason for these. One characteristic of nickel-cadmium batteries is that different than the lead-acid batteries, the nickel-cadmium will not dissolve into the electrolyte as the lead-acid does in these type of batteries. So most of the failure modes that can be detected in the lead-acid batteries, because the active material, the lead, is dissolving into the electrolyte and changing the ohmic value, this is not going to be able to be detected that easily in the nickel-cadmium batteries. There's a few failure modes in nickel-cadmium batteries that will definitely affect the ohmic value of the cell, but it's not going to be many of them, and the actual main interest of the ohmic testing is to determine the aging or the loss of capacity of the battery, or try to correlate that in a certain way to the ohmic value. So in these nickel-cadmium batteries, that doesn't happen, and a nickel-cadmium battery definitely can show an increased ohmic value when it is out of capacity or when it's already a battery that it's not good anymore. However, this is not going to be always. You could have a battery under that condition with no capacity or in very bad condition, but the ohmic value is going to be the same as when it was new. So it's not such a reliable test for nickel-cadmium on certain cases. So I guess that's my thinking about why they remove it from there. Thanks.
All right, next question. If the battery is operated at elevated temperatures and the life of the battery has to be reduced, is the expected service life also reduced? Should the annual performance test be done when this new expected service life is reached?
The service life that's provided by the manufacturer is provided on the basis that the batteries will be operated at 25 Celsius or at a standard temperature. Temperature plays a major role in the life of the battery. If the batteries are stored at a low temperature, then that slows down the chemical process in the battery. If they're operated at a high temperature, then that causes deterioration in the battery, and the service life is reduced, as you said. But I don't think it's possible to get a number based on the temperature. So what you really need to look at is how is the capacity changing, and when the capacity starts degrading and gets to that point when you need to switch to annual testing, that's when you'll switch to annual testing. So you don't necessarily need to go with. There is no way to get an expected service life just based on the temperature at which the batteries are stored. Just try to keep it as close to 25 Celsius as possible, so that the service life is close to what the expected service life is that's provided by the manufacturer.
All right, next question. Please share some details on low duty cycle versus battery duty cycle.
Well, the manufacturers, they, I guess from this question, what the person that asked this question is referring to the battery duty cycle is what the manufacturer can offer on the battery. So the battery will have these tables, and it will show what the constant currents can the battery do. And well, that is totally different from the load duty cycle that is going to be happening at the substation or the facility, whatever the battery is connected. And the designer, according to those criteria and those parameters that I mentioned in one of the slides about the aging factor, the service factor, the temperature, all of these considerations, the designer is going to request for a battery or is going to ask for a battery that is capable to cover all of that duty cycle. So, of course, there's a difference there, and the idea is that whatever battery is installed, it's going to be able to handle that duty cycle in the battery in the substation.
All right, thank you. Next question. The temperature of the capacity test is the temperature of the electrolyte, not the ambient, correct?
Yes, that's true. So you need to look at the temperature of the cells. Under normal operation, the temperature of the batteries will pretty much be the same as the temperature of the room, but as the battery discharges during the process, the batteries might get a little warmer. So yes, an accurate way of assessing the batteries is to look at the temperature of the batteries and not just temperature of the room.
All right, next question. Do decay rates change with the increase or decrease of discharge rate? As such, should testing be increased from annually? Is there such a thing as overtesting?
So definitely there could be something such as overtesting, and that's why the recommendation from the standard. However, if you consider that your maintenance procedures might not be as effective as you think, and you want to check if the battery is really deteriorating, well, you may be able to run a test, or you want to run a test to confirm that. So again, all of these relates to the amount of cycles and the conditions of the battery. So yes, there can be overtesting, but the idea is to have a good trending of the battery and gather the most information that you can every time you do a maintenance. The other thing to consider is that the other part of the question was about the rates. So rate has to be the same. The rate of discharge has to be the same every time you test, so you can compare the results. Of course, you can change the rate, but it's not going to be a comparable value to whatever you had previously. And the other thing that you can consider is instead of running a performance test, you want to probably just check that the battery can do whatever you are expecting it to do, which is the service test.
All right, what is your opinion of conductance testing versus capacity testing?
So when we talk about conductance testing in the standards or the guides, the term ohmic testing is used, and there are different ways of doing ohmic testing. What we promote is impedance testing, that there's also conductance testing or resistance testing done. So if I had to talk about impedance testing versus capacity testing, both look at two different things. Impedance testing is a check of the electrical path in the system. So what you do is you measure the impedance of the cells, you measure the resistance of the straps connecting those cells, you measure the DC voltage. So you basically get an idea of the condition of the electrical path. If there is let's say if there is deterioration on the plates, if there's corrosion on the plates, you will get higher strap resistances. If there is anything happening inside the cell, you might get higher impedance values. If there are shorted cells inside, you might get lower impedance values. So that kind of information is provided by impedance testing. Capacity testing, on the other hand, it gives you an idea of the true capacity of the battery, right? So you are actually drawing current from the battery, which is ultimately the objective of the battery. The battery is supposed to provide power to the loads in the case of an outage. So you are simulating an outage. You are drawing a certain current from the battery, and you're observing whether the battery will be able to provide a sustained power to the load for the duration that it's supposed to. So capacity testing is of higher value as compared to impedance testing, but in a good maintenance program, you can have both tests complementing each other. Capacity testing requires a lot of effort and time. You need to have backup batteries in case you don't have one. You need to make arrangements for those to be able to do testing. So on the other hand, impedance testing is easier to carry out. You don't need to take the battery off service. It's still online. You're just taking measurements on the battery bank. So impedance testing can be done more frequently at regular intervals in between capacity tests. So even when you're not doing a capacity test, you're still tracking the condition of the battery, and you still have some information in the intervals between capacity tests. So you can have both tests as part of your battery maintenance program.
All right. Do you prefer adjusting rate or time based on temperature?
So from this is referring to the two methods that are available to calculate the capacity, and the main aspect is not probably about preference, but it's about how long is the test going to be, or what is the expectation of the duration of the test. So as indicated during the presentation, the time-adjusted method is for tests longer than 1 hour, and the recommended method for tests shorter than 1 hour is the rate-adjusted method. However, the rate-adjusted method is will come up with higher accuracy results, and it can be used also for the time-adjusted or for tests longer than 1 hour. So the difficulty there is that you need to consider for the rate-adjusted method the aging factor of the battery. You can assume 80% is the aging factor of the battery. However, this is better to have information from the manufacturer, and sometimes this is not easy to get, or the method itself includes or considers some or has some difficulties. So people used to prefer to use the time-adjusted method, which is easier to use and to apply.
All right, next question. In a battery bank, while performing a capacity test, say batteries number 18 of 60, voltage drops very low. You abandon the test or continue? How should we prepare for a retest? Replace number 18 first, or are other options available?
So during a capacity test, the guide allows you to pause the test. The period is called a downtime period. So you're allowed to pause the test once during the duration of the test, and the maximum duration of downtime allowed is 6 minutes, basically. So in this 6 minutes pause, you get to decide when you pause the test. Only one pause is allowed, but you get to decide when to do that. So it's entirely up to you. If you have the right equipment, you will be able to monitor individual cell voltages continuously in real time. And when you see a cell approaching polarity reversal, which is 1 volt, that's when you can choose to take a downtime. And if you have multiple cells approaching that condition, you can bypass multiple cells. So it's up to you how you go about it. When you take that pause is also up to you. So you'll need to monitor the cell voltages continuously to be able to do that, to be able to choose the best time to take that pause. So what you will do is if you pick out the cells that you need to bypass, you'll take that downtime and you will bypass those cells, and then you can resume the test and then continue. But what you will need to do is, and this is one of the other questions that has been asked by one of our listeners, you will need to change the end voltage now, because now if you have taken 2 cells out of the equation, then you have 58 cells. So the end voltage is going to change based on that. So it might be 58 times 1.75 instead of 60 times 1.75. So that needs to be done.
Okay. Next question. Why measure floating voltage? The float voltage is simply a result of the battery charger output. The open circuit voltage will be less than float voltage. Wouldn't this be the more appropriate voltage to refer to?
So definitely the open circuit voltage is very important. And as I mentioned briefly during the presentation, one of the reasons to measure the float voltage is that you can compare, you can see if there's any drastic drop in the voltage of the cell when you disconnect the charger. So if there's any difference or high difference between the float voltage and the open circuit voltage, this might be an indication that the battery or that specific cell might not perform well during the test. So probably before you even starting the test, you can bypass that cell or you can take some actions before running the test. So it's kind of a very comprehensive test that you are running here. You're not just running the test to measure the capacity, and that's why I was also mentioning that there's a lot of information in the test that you can use to analyze your results farther or beyond the capacity result. Another thing to consider is that the float voltage it's really a test on the charger. You are verifying that your charger is properly set. Battery that it's not charged at the right voltage might be affected by that condition. So you can accelerate one of the failure modes, which is the corrosion, positive plate corrosion, if the battery is overcharged or floating at a higher voltage than the recommended. Or you can also accelerate the sulfation failure mode, which is the condition of a battery that is undercharged. So as a person that is going to review the result or a test report that was not present at the moment of the test, you want to know what is the condition of the charger, what is the condition of the cells prior to starting the test, and that's what these two measurements will give you. So you have very good criteria when reviewing the result and when reviewing the report.
All right, next question. Can the battery charger alone supply all the DC loads momentarily? Is it acceptable to supply all DC loads with the charger only, say, for 1 hour without the backup or standby battery connected?
So yes, the battery charger is supposedly capable to do the entire load of the substation, and that's what actually it does when it is under normal operation. The charger is supplying the load, and it's supplying a little bit more so it can maintain the charge on the battery. So that's what the floating condition is, that it will supply voltage and current for the load and the battery at the same time. So yes, the charger can be used to support the substation or the facility when the battery is not there, but then you're risking if something happens, if there's any power failure, you're going to lose the charger and you're going to lose the facility because there's no battery to support that. So that's when the need of the backup battery comes in, depending on the criticality of your installation, or if you definitely cannot have the load without any power, you don't want to risk that. So you want to install a temporary backup.
All right, next question. When performing the capacity test or load test, is the battery totally disconnected from the DC system?
So as Volney just said, it's important to have a backup battery if you're just to be safe from an outage. But let's say you have a load, you don't have a backup battery, and you want to do a discharge test on a battery bank. You can do that. The battery will be disconnected from the charger, of course, because you don't want to be discharging the battery while it's being charged at the same time, right? So you will need to disconnect the charger, but it can still be connected to a load while I can speak for the equipment that we make. You can have a CT with which you can measure the current that's being drawn by the load, and then whatever current we need to draw for the discharge test, the CT will measure the current that's being drawn by the load, and that will be subtracted from the current that we need to draw during the discharge test. So the load bank will draw the remaining amount of current, and that current will be regulated as the test progresses. So you don't need to be disconnected from everything. You need to be disconnected from the charger, but whatever the current that is being drawn by the load during the discharge test, the load in your system, that can be taken into account, and that can be included as part of the discharge test current.
All right, the next question. Does the Megger torque unit allow you to change your end of test voltage mid-test in the event you need to pause the test to bypass a defective cell?
Yes, and this again goes back to a couple of questions ago when we talked about taking the downtime or pausing the test for 6 minutes. When you do that, when you take the cells out, you need to adjust the end voltage based on the number of cells that you have taken out. And yes, our software allows you to do that at any point during the test. You can change the warning limits or the stop limits. That can be done while the test is on.
All right, thank you, Sanket. Unfortunately, we have hit our 1.5 hour mark with our 30-minute Q&A session now. We have actually received almost 80 questions. So what we're going to do is we're going to try and get back to answering these questions and get some answers out to you guys. But at this time, we're going to go ahead and close the webinar. Again, you will receive a copy of the presentation today, as well as a link to this video, so you can go back and watch the recording at any time later on or share it with your colleagues. We'd like to thank you all for attending, and hope you have a great weekend.